Welcome. Thank you for joining the Z-Files as we drift into a quiet exploration of one of humanity's most steadfast dreams, harnessing the power of a star. In the coming hour or so, we will calmly trace the physics, the experiments, the human-scale implications, and the perceived dangers of nuclear fusion, sharing surprising facts and gentle reflections as you unwind. Part 1. The Dream of Starlight. Imagine for a moment the sun, not as a distant disk of light, but as a furnace. Deep in its core, hydrogen atoms collide with such force that they merge, fusing into helium and releasing energy that has warmed our world for billions of years. This is fusion, the process that powers every star in the night sky. It is vast, and it has captivated human imagination since we first understood what makes stars shine. For nearly a century, scientists have dreamed of bringing that stellar fire to Earth. Not to destroy, but to create. To build what some call a miniature sun, a controlled fusion reactor that could generate clean, abundant energy without the long-lived radioactive waste of conventional nuclear power or the carbon emissions of fossil fuels. It is an audacious vision, one that has consumed billions of dollars, decades of research, and the careers of thousands of brilliant minds. Yet fusion power remains, as of now, a promise rather than a reality. The appeal is not difficult to understand. Fusion fuel is plentiful. The primary ingredients, deuterium and tritium, can be extracted from seawater and lithium. A single bathtub of seawater contains enough deuterium to match the energy of 300 gallons of gasoline. The waste products are far less problematic than those from fission reactors, the kind that split atoms rather than merge them. And unlike coal or natural gas, fusion produces no greenhouse gases during operation. If we could harness it, fusion might remake our relationship with energy itself. But the path from dream to reality is steep. Fusion requires conditions so extreme that they exist naturally only in the cores of stars. Temperatures exceeding 100 million degrees Celsius, pressures that crush matter into plasma, and confinement schemes delicate enough to hold that plasma steady while it burns. On Earth, we lack the crushing gravity of a star. We must rely on ingenuity, on magnetic fields or laser pulses, on materials that can withstand punishment no natural substance was meant to endure. This is the story of that pursuit. It is not a tale of simple triumph, nor of certain failure. It is a chronicle of incremental progress, setbacks, breakthroughs, and the patient, grinding work of science at its most ambitious. Over the course of this narrative, we will explore how fusion works, why it is so difficult to achieve, and where researchers stand in their quest to ignite a controlled stellar fire. We will visit the great experimental facilities scattered across the globe, from the Tokamaks of China and Europe to the laser chambers of California. We will examine the physics, the engineering, the economics, and the human stakes of this endeavor. Fusion and fission are often confused, so let us clarify. Fission, the process used in today's nuclear power plants, splits heavy atoms like uranium or plutonium into lighter fragments, releasing energy in the process. It works, it generates power reliably, but it also produces long-lived radioactive waste and carries risks that have been etched into public memory by accidents at Chernobyl and Fukushima. Fusion, by contrast, merges light atoms into heavier ones. The fuels are isotopes of hydrogen. The primary byproduct is helium, an inert, harmless gas. Neutrons are released, and they do cause some material activation, but the waste is far less radioactive and decays much faster than fission waste. There is no chain reaction to run away, no meltdown scenario. If the confinement fails, the plasma simply cools and the reaction stops. This difference matters. It shapes how the public perceives fusion, how governments fund it, and how researchers frame their work. Fusion is often called the clean nuclear option, the one that might finally reconcile our hunger for energy with our need to protect the planet. Whether that promise can be fulfilled is the question that drives this exploration. As we begin, know that the story of fusion is not just one of machines and equations. It is also a story of persistence, of scientists who have devoted entire careers to a goal that may not be realized in their lifetimes. It is a story of international collaboration and competition, of nations pouring resources into machines that may or may not succeed. And it is a story of hope, quiet and stubborn, that we might one day light our cities with the same fire that lights the stars. Let us step, then, into that story. Let us wander through the physics, the experiments, the dreams and difficulties of fusion energy. Let us see what it takes to build a star on Earth. In the parts that follow, we will unpack the science piece by piece, gently and thoroughly, so that by the end you will understand not just what fusion is, but why it remains so tantalizingly out of reach, and why so many believe it is worth chasing. Part 2. The Physics of Merging Atoms. To understand why fusion is difficult, we must first understand what fusion is. At its heart, the process is simple. Take two light atomic nuclei and bring them close enough that the strong nuclear force, which binds protons and neutrons together, overcomes the electric repulsion between their positive charges. When that happens, the nuclei can merge, forming a heavier nucleus and releasing energy in the process. This energy comes from a famous equation, Einstein's equals mc squared. When light nuclei fuse, the mass of the resulting nucleus is slightly less than the combined mass of the original nuclei. That missing mass has been converted into energy, a staggering amount of energy given the speed of light squared. A single fusion reaction releases millions of times more energy per reaction than a chemical bond breaking, like the combustion of gasoline or coal. The challenge lies in overcoming that electric repulsion. Atomic nuclei are positively charged. Like charges repel. To merge them, you must slam them together with enormous force, which means heating them to extreme temperatures. In the Sun, gravity provides the pressure, and the core reaches about 15 million degrees Celsius. On Earth, without that gravitational advantage, we must go even hotter, typically exceeding 100 million degrees, to achieve useful fusion rates. At such temperatures, matter exists as plasma, a fourth state beyond solid, liquid, and gas. In plasma, electrons are stripped from their atoms, leaving a seething mix of ions and free electrons. This plasma is electrically conductive and responsive to magnetic fields, properties that researchers exploit to confine and control it. But plasma is also wild, unstable, prone to turbulence and instabilities that can disrupt the fusion process. The most common fusion reaction pursued on Earth involves deuterium and tritium, two isotopes of hydrogen. Deuterium has 1 proton and 1 neutron. Tritium has 1 proton and 2 neutrons. When a deuterium nucleus fuses with a tritium nucleus, they form a helium nucleus, also called an alpha particle, and release a high-energy neutron. This reaction, often written as DT fusion, occurs more readily than other fusion reactions at the temperatures we can achieve in laboratories. Deuterium is abundant. It occurs naturally in seawater, roughly 1 atom in every 6,500 hydrogen atoms. Extracting it is straightforward and inexpensive. Tritium, however, is scarce. It is radioactive, with a half-life of about 12 years, and occurs in nature only in trace amounts. For fusion reactors, tritium must be bred. The plan is to surround the reactor with a blanket containing lithium. Neutrons from the fusion reactions strike lithium, producing tritium, which can then be extracted and fed back into the reactor. This breeding cycle is essential for sustained fusion power, and developing efficient breeding blankets is one of the major engineering challenges facing the field. Beyond DT fusion, researchers have explored other reactions. Deuterium-deuterium fusion requires higher temperatures but produces no tritium and generates fewer high-energy neutrons. Proton-boron fusion is even cleaner, producing only helium and no neutrons, but it demands temperatures and confinement conditions far beyond current capabilities. For now, DT remains the most practical target. The measure of success in fusion is energy gain, expressed as Q. Q is the ratio of fusion power output to heating power input. The Q of 1 means you get out as much energy as you put in, break even. A Q greater than 1 means net energy gain. For practical power generation, you need a Q well above 1, typically 10 or higher, to account for inefficiencies in converting fusion energy to electricity and powering the reactor systems. Achieving net energy gain requires satisfying the Lawson criterion, named after physicist John Lawson. The criterion states that for a fusion reaction to be self-sustaining, the product of plasma density, confinement time, and temperature must exceed a certain threshold. In simpler terms, you need enough particles, held together long enough, at a high enough temperature, for fusion reactions to release more energy than is lost through radiation and particle escape. There are 2 main approaches to meeting the Lawson criterion: magnetic confinement and inertial confinement. Magnetic confinement uses powerful magnetic fields to trap plasma in a donut-shaped chamber, holding it away from the walls and allowing it to burn for seconds or even minutes. Inertial confinement compresses a tiny fuel pellet with intense laser or ion beams, creating conditions so extreme that fusion occurs in a brief, intense pulse lasting billionths of a second. Each approach has strengths and weaknesses. Magnetic confinement offers longer burn times and steadier operation, but the machines are enormous, complex, and expensive. Inertial confinement produces higher densities and temperatures, but repeating the pulses rapidly enough for continuous power generation is a daunting challenge. The pursuit of fusion has been marked by both optimism and frustration. Early predictions in the 1950s and 60s suggested fusion power might arrive within decades. Those predictions proved wildly optimistic. The plasma proved more turbulent, the engineering more demanding than anyone anticipated. Progress has been real but slow, measured in incremental gains rather than sudden leaps. Still, the physics is sound. Fusion works. We have achieved fusion in laboratories many times. The question is not whether fusion is possible, but whether we can make it practical, economical, and reliable. As we move forward, we will see how different projects around the world are tackling these challenges, each with its own strategy and timeline, each contributing pieces to the puzzle of controlled fusion energy. Part 3: Magnetic Cages and Tokamak Giants. The Tokamak is the workhorse of magnetic fusion research. The name comes from Russian, a contraction meaning toroidal chamber with magnetic coils. Picture a hollow donut, its interior filled with plasma held suspended by powerful magnetic fields. The plasma never touches the walls. If it did, it would cool instantly, the fusion reactions would cease, and the wall material would contaminate the plasma. The magnetic fields form invisible cages, twisting and looping in precise geometries to keep the plasma stable and hot. The Tokamak concept emerged in the Soviet Union during the 1950s, developed by physicists Igor Tamm and Andrei Sakharov. Early experiments showed promise, and by the 1960s, Soviet tokamaks were achieving plasma temperatures and confinement times that surpassed Western designs. The results were initially met with skepticism, but visiting scientists confirmed them, and the tokamak became the dominant approach worldwide. Today, dozens of tokamaks operate across the globe, each pushing different aspects of the fusion challenge. Some focus on sustaining plasma for longer durations. Others test new materials or magnetic configurations. A few aim for the ultimate goal, ignition, the point where the fusion reactions produce enough heat to keep the plasma burning without external input. The largest and most ambitious tokamak under construction is ITER, the International Thermonuclear Experimental Reactor, being built in southern France. ITER is a collaboration among 35 nations, including the European Union, the United States, China, Russia, India, Japan, and South Korea. It is massive, standing as tall as a 10-story building, with a plasma volume of 840 cubic meters. The machine uses superconducting magnets cooled to near absolute zero, generating magnetic fields strong enough to confine plasma heated to over 150 million degrees Celsius. ITER's goal is to achieve a Q of 10, meaning it will produce 10 times more fusion power than the heating power required to sustain the plasma. If successful, it will be the first fusion device to demonstrate net energy gain at a scale relevant for power generation. The project has faced delays and cost overruns, common in endeavors of such complexity. First plasma, originally expected around 2020, is now anticipated in the late 2020s, with full fusion operations in the 2030s. The timelines are long, the budget measured in tens of billions of dollars, but ITER represents a collective bet that fusion is achievable. While ITER builds toward the future, other tokamaks have already set records. The Joint European Torus, or JET, located in the United Kingdom, held the previous record for fusion energy output. In experiments conducted in 2021 and again in early 2022, JET produced 59 megajoules of fusion energy over a 5-second pulse, more than doubling its own 1997 record. JET uses the same DT fuel mixture planned for ITER, and its results provided crucial validation of the physics models ITER relies upon. JET concluded its operations in late 2023, having served the fusion community for 4 decades. China has invested heavily in fusion research, operating several significant tokamaks. The experimental advanced superconducting tokamak, known as EAST, is sometimes called the Chinese artificial sun. Located in Hefei, EAST is fully superconducting, allowing it to sustain plasmas for much longer than machines using conventional magnets. In recent years, EAST has set records for plasma duration. In 2021, researchers reported maintaining a plasma at temperatures exceeding 120 million degrees Celsius for over 1,000 seconds, roughly 17 minutes. This achievement demonstrated progress toward the steady-state operation that a practical fusion power plant would require. China also operates the HL-2M tokamak, often referred to as the new generation artificial sun. It began operations in late 2020 and focuses on achieving higher plasma temperatures and testing advanced confinement scenarios. These Chinese efforts are part of a broader national strategy to position China as a leader in fusion energy research, with substantial government funding and ambitious timelines. In the United States, several tokamaks continue to contribute. The DIID National Fusion Facility in California studies plasma physics and tests configurations that might improve stability and confinement. DIID has explored advanced scenarios like the high confinement mode, or H mode, where the plasma spontaneously forms an edge transport barrier that reduces energy losses. Understanding and controlling H mode is critical for ITER's success. Not all magnetic confinement devices are tokamaks. The Stellarator, another magnetic confinement concept, uses a twisted, pretzel-like geometry to confine plasma without requiring the large electrical currents that flow through tokamak plasmas. These currents are a source of instability in tokamaks. Stellarators avoid them by shaping the magnetic coils themselves in complex, three-dimensional curves. The most advanced stellarator operating today is Wendelstein 7X, located in Greifswald, Germany. It began experiments in 2015 and has steadily improved its performance. Wendelstein 7X is not designed to achieve fusion, but to demonstrate that stellarators can confine plasma as well as tokamaks while avoiding certain instabilities. Recent experiments have shown promising confinement and steady-state potential, suggesting that stellarators might offer an alternative path to fusion energy, though their complex engineering presents its own challenges. Private companies have also entered the fusion race, bringing new urgency and funding models. Commonwealth Fusion Systems, or CFS, spun out of MIT, is building a compact tokamak called Spark. Spark will use high-temperature superconducting magnets, a recent technological advance that allows for much stronger magnetic fields in a smaller device. CFS aims to demonstrate net energy gain in the mid-2020s, ahead of ITER, and then proceed to a commercial pilot plant called ARC. The company has raised over $2 billion, a sign of growing private sector confidence in fusion's potential. These are just a few of the players in the magnetic confinement field. Each machine, each experiment adds data to the collective understanding of plasma behavior. Progress is collaborative, even when competitive. Results are shared at international conferences, published in journals, scrutinized and built upon. The magnetic confinement community is large, diverse, and patient, working toward a goal that may still be decades away. Yet the Tokamak is not the only path. Another approach, fundamentally different, seeks to achieve fusion not through sustained confinement but through sudden, violent compression. Part 4. Inertial confinement and the ignition milestone. Inertial confinement fusion, or ICF, takes a different route to the same destination. Instead of holding plasma steady for seconds or minutes, ICF compresses a tiny capsule of fusion fuel to extraordinary densities and temperatures for a fleeting instant. The compression happens so quickly that the fuel's own inertia, its resistance to sudden motion, holds it together just long enough for fusion to occur. The entire event lasts nanoseconds, billionths of a second, but in that brief flash, conditions rival those in the core of a star. The primary facility pursuing ICF in the United States is the National Ignition Facility, or NIF, located at Lawrence Livermore National Laboratory in California. NIF is the world's largest and most energetic laser system. It occupies a building the size of 3 football fields. At its heart is a target chamber 10 meters in diameter, into which researchers place a fuel capsule smaller than a peppercorn. That capsule contains a mixture of deuterium and tritium, frozen into a thin shell inside a cylindrical container called a Hall-ROM. When the experiment begins, 192 powerful laser beams converge on the Hall-ROM from all directions. The lasers do not strike the fuel capsule directly. Instead, they heat the Hall-ROM's inner walls, causing them to emit intense X-rays. These X-rays bathe the fuel capsule uniformly, ablating its outer layer. As the outer material explodes outward, the remaining fuel is driven inward by Newton's third law, compressing it to incredible densities, more than 100 times the density of lead, and heating it to over 100 million degrees. If the compression is symmetrical and the conditions are right, fusion ignites. The alpha particles produced by the fusion reactions deposit their energy in the surrounding fuel, heating it further and triggering more fusion. This is called ignition, the point where the fusion process becomes self-sustaining within the compressed fuel, if only for an instant. For decades, ignition remained elusive. NIF began operations in 2009 with a goal of achieving ignition within a few years. The target proved more difficult than anticipated. Small asymmetries in the compression, instabilities in the fuel shell, and energy losses all conspired to prevent ignition. Researchers refined their techniques, adjusted laser pulse shapes, improved capsule fabrication, and ran countless simulations. Then, in December 2022, NIF achieved a historic breakthrough. In a single experiment, the fusion reactions produced more energy than the laser energy delivered to the target. Specifically, the lasers delivered just over 2 megajoules to the Hull ROM, and the fusion reactions released about 3.15 megajoules. This was the first time, anywhere, that a controlled fusion experiment had crossed the threshold of fuel energy gain, a milestone researchers had pursued for more than 50 years. The achievement was announced publicly in December 2022, and the scientific details were published in peer-reviewed journals in early 2023. The result was independently confirmed. It represented a genuine scientific breakthrough, demonstrating that ignition in a laboratory setting is possible. However, the celebration came with caveats. The energy delivered to the target, about 2 megajoules, was only a small fraction of the total energy consumed by the facility. The lasers themselves are inefficient, requiring about 300 megajoules of electrical energy to produce the 2 megajoules of laser light. So while the fusion output exceeded the laser input, it fell far short of the total energy cost. Achieving practical power generation with ICF would require dramatic improvements in laser efficiency, repetition rate, and target manufacturing. NIF was not designed as a prototype power plant. It was built primarily for stockpile stewardship, to study nuclear weapons physics without underground testing. Fusion ignition serves both that mission and the broader goal of energy research. The facility demonstrated proof of principle, but translating that principle into a power plant is a separate, formidable challenge. Following the December 2022 milestone, NIF repeated the achievement in subsequent experiments, refining the process and increasing the energy yield. In July 2023, they reported an experiment producing approximately 3.88 megajoules, and further experiments in late 2023 and into 2024 continued to push yields higher, with some experiments reportedly exceeding 4 megajoules. These repeated successes showed that the ignition result was reproducible, not a fluke, and that researchers were gaining better control over the process. Other countries and private companies are pursuing ICF as well. In China, research facilities under the Chinese Academy of Sciences are developing high-power laser systems aimed at fusion energy research, though details of their progress are less widely publicized. Private companies like TE Technologies and First Light Fusion in the United Kingdom are exploring alternative approaches to inertial fusion, using different drivers like particle beams or projectile impact instead of lasers. The challenge for ICF is scaling. A power plant would need to compress and ignite fuel capsules many times per second, perhaps 10 or more, to generate continuous power. Each capsule must be manufactured to exacting tolerances, positioned precisely, and injected into the target chamber. The debris from each micro-explosion must be cleared before the next shot. Lasers or other drivers must be efficient, reliable, and capable of firing repeatedly without degradation. These are engineering challenges of a high order. Some researchers envision hybrid approaches, combining aspects of magnetic and inertial confinement. Others propose entirely different schemes, such as magnetized target fusion, where plasma is first confined magnetically and then compressed rapidly by external pressure. The field is diverse, exploratory, and far from settled on a single best path. What is clear is that fusion ignition, once a distant dream, is now a demonstrated reality. The physics works. The question, as always, is whether the engineering, economics, and timelines can align to make fusion a practical source of power. The NIF result energized the field, attracted new investment, and renewed public interest. It also underscored how much work remains. As we turn next to the deeper engineering challenges, the materials and systems that must withstand the punishing environment of a fusion reactor, we will see that ignition is just one milestone on a long road. The path from scientific achievement to commercial deployment is strewn with obstacles, each requiring innovation, persistence, and resources. Part 5. The Engineering Gauntlet. Achieving fusion in a laboratory is one thing. Building a machine that can sustain fusion reactions continuously, extract the energy safely, and operate reliably for years is another matter entirely. The engineering challenges are formidable, touching every aspect of materials science, thermodynamics, remote handling, and system integration. A fusion power plant must confine plasma hotter than the sun's core, extract heat from neutrons traveling at 1/5 the speed of light, breed its own fuel, and do all this without degrading or failing under conditions no conventional power plant has ever faced. Consider the neutrons. In DT fusion, roughly 80% of the energy released appears as kinetic energy of the neutron. These neutrons are not confined by magnetic fields. They stream outward from the plasma, passing through the first wall of the reactor and into the surrounding blanket. This is by design. The neutrons carry energy that must be captured and converted to heat, which then drives turbines to generate electricity. But neutrons also cause damage. High-energy neutrons collide with atoms in the reactor's structural materials, knocking them out of their lattice positions and creating defects. Over time, these defects accumulate. Metals become brittle, their mechanical properties degrade, and they swell. This process is called neutron embrittlement, and it limits the lifetime of reactor components. In a fusion power plant operating continuously, the first wall and blanket structures would need to withstand neutron fluences far exceeding anything experienced in fission reactors. Materials scientists are working to develop radiation-resistant alloys. Reduced activation ferritic martensitic steels, often abbreviated as RAFM steels, are one candidate. These steels are designed to minimize the production of long-lived radioactive isotopes when bombarded by neutrons, so that decommissioned reactor components become less hazardous more quickly. Tungsten, with its high melting point and low erosion rate, is being tested for plasma-facing surfaces. Advanced ceramics and composite materials are also under investigation. Testing these materials is difficult. Existing fission reactors and spallation neutron sources can simulate some of the neutron damage, but the neutron energy spectrum in a fusion reactor is different. The 14 million electron-volt neutrons from DT fusion are more energetic than most fission neutrons. Purpose-built fusion neutron sources, sometimes called fusion prototypic neutron sources, are needed to fully qualify materials, but such sources do not yet exist. ITER will provide some data, but a dedicated materials testing facility, possibly a smaller fusion reactor optimized for high neutron flux, may be necessary before commercial fusion plants can be designed with confidence. Beyond materials, the blanket must perform multiple functions. It must capture neutron energy and convert it to heat. It must breed tritium from lithium to sustain the fuel cycle. And it must shield the superconducting magnets and other sensitive components from neutron radiation. Designing a blanket that does all this efficiently is a complex optimization problem. Several blanket concepts are being explored. Liquid metal blankets use flowing lithium or lithium lead alloys to absorb neutrons and breed tritium while transferring heat. Solid breeder blankets use lithium-containing ceramics, with a separate coolant flowing through channels to extract heat. Molten salt blankets, where lithium salts serve as both breeder and coolant, are another option. Each approach has trade-offs involving tritium breeding ratio, heat extraction efficiency, chemical compatibility, and ease of maintenance. Tritium breeding is critical. Natural sources of tritium are insufficient for fusion power. Each reactor must produce at least as much tritium as it consumes, ideally more to account for losses and to supply fuel for starting up new reactors. Achieving a tritium breeding ratio greater than 1 requires careful neutron economy, optimizing the blanket composition and geometry to maximize the likelihood that neutrons interact with lithium rather than being absorbed elsewhere or escaping. Extracting tritium from the blanket is another challenge. Tritium is radioactive and must be handled carefully. It can diffuse through metals and permeate containment barriers. Recovery systems must continuously remove tritium from the blanket materials or coolant, purify it, and return it to the fuel cycle. Losses must be minimized, both for economic reasons and to limit environmental release. Heat exhaust is equally daunting. In a tokamak, the plasma is hottest in the core and cooler at the edge. The temperature gradient drives heat flow outward. Ideally, this heat would spread evenly over the reactor's inner surfaces, but magnetic field geometry tends to concentrate the exhaust heat onto a narrow region called the diverter. The diverter is where plasma particles, guided by magnetic field lines, strike a solid surface and are neutralized, removing heat and impurities from the plasma. Diverter surfaces experience power loads that can exceed 10 megawatts per square meter, comparable to the heat flux at the surface of the Sun. No material can withstand such conditions indefinitely without erosion or melting. Tungsten, the leading candidate material, can handle high heat fluxes but still suffers erosion over time. Cooling the diverter efficiently, without disrupting the plasma or compromising structural integrity, requires sophisticated engineering. Advanced diverter concepts aim to spread the heat more evenly or to radiate it away before it strikes solid surfaces. The Super X diverter, the snowflake diverter, and liquid metal diverters are among the ideas being tested in experimental tokamaks like MASTU in the United Kingdom and DIIID in the United States. These concepts show promise in simulations and small-scale experiments, but validating them at reactor scale remains an open question. Superconducting magnets, essential for magnetic confinement fusion, present their own challenges. These magnets must generate fields of several Tesla while operating at cryogenic temperatures, typically around 4 degrees above absolute zero. The magnets are massive, weighing thousands of tons, and must be precisely manufactured and assembled. They are also expensive, representing a significant fraction of a reactor's capital cost. Recent advances in high-temperature superconductors, which operate at somewhat higher temperatures than conventional low-temperature superconductors, offer the possibility of stronger fields in more compact devices. This is the approach Commonwealth Fusion Systems is taking with Spark. High-temperature superconductors, typically made from rare earth barium copper oxide, or REBCO, can carry higher current densities and tolerate higher magnetic fields than niobium tin or niobium titanium, the conventional superconducting materials. This allows for smaller, less expensive reactors with improved performance. However, REBCO tapes are still relatively new, and manufacturing them at the scale and quality required for fusion magnets is an ongoing industrial challenge. The materials are brittle, sensitive to strain, and expensive. Joining them, protecting them from quench events where superconductivity suddenly fails and the magnet heats up, and integrating them into large magnet systems all require careful engineering. Remote maintenance is another necessity. Once a fusion reactor has operated with tritium and high neutron fluxes, many components become radioactive. Humans cannot enter the reactor hall without prohibitive radiation exposure. All maintenance, repair, and replacement of components must be done remotely, using robotic systems and automated tools. Designing a reactor that can be serviced this way, with components that can be extracted, replaced, and reassembled by machines, adds layers of complexity to the design. ITER is pioneering remote handling techniques, developing specialized tools and procedures to maintain its vast array of in-vessel components, blanket modules, and diverter cassettes. These lessons will be invaluable for future reactors, but they also illustrate how much more difficult fusion maintenance is compared to conventional power plants. The integration of all these systems, plasma physics, magnets, blankets, diverters, tritium handling, remote maintenance, heat extraction, and power conversion into a coherent, reliable machine is the central engineering challenge of fusion. It requires not just solving individual problems but ensuring that the solutions work together, that the system as a whole is robust, economical, and safe. This is why fusion has taken so long. This is why predictions made decades ago proved too optimistic. The physics, though challenging, was understood in principle relatively early. The engineering, the relentless accumulation of practical knowledge and technological capability, has taken far longer than anyone anticipated. Yet progress continues, piece by piece, system by system, as we shall see in the next part when we turn to the economics and the question of whether fusion can ever be commercially viable. Part 6. The Economics of Starfire. All the scientific breakthroughs and engineering triumphs in the world mean little if fusion power cannot compete economically. Energy is, at its core, a commodity. Consumers and industries care about cost, reliability, and availability. A fusion power plant must generate electricity at a price competitive with solar, wind, natural gas, and fission, or it will remain a curiosity, a demonstration project rather than a solution. The economics of fusion are uncertain, in part because no commercial fusion reactor has ever been built. Estimates of the cost to build and operate such a plant vary widely, depending on assumptions about technology maturity, materials costs, construction timelines, and financing. Some projections suggest fusion electricity could be competitive with other low-carbon sources within a few decades. Others are more pessimistic, pointing to the massive capital costs and technical uncertainties that remain. ITER, though not a power plant, provides a sobering reference point. The project's cost has escalated over the years, now estimated at over 20 billion euros, shared among the partner nations. ITER will not generate electricity for the grid. It is a research facility designed to demonstrate net energy gain and to test technologies needed for a future demonstration power plant, often called demo. Demo, in turn, would be a prototype, proving that continuous electricity generation from fusion is feasible. Only after demo would commercial plants be built. This staged approach is prudent but slow and expensive. If each step takes a decade or more, commercial fusion power remains decades away. Some argue that the timeline is too long, that climate change and energy demand require faster solutions. Others counter that fusion is a long-term investment, a technology for the second half of this century and beyond, not a near-term fix. Private companies, flush with recent investment, are attempting to accelerate the timeline. Commonwealth Fusion Systems, TE Technologies, Helion Energy, and others have raised billions of dollars collectively, aiming to build smaller, less expensive reactors and to reach commercial operation in the 2030s. These companies often eschew the incremental, publicly funded model in favor of rapid iteration, leveraging advances in materials, magnets, and computational design. Helion Energy, for instance, is pursuing a pulsed, non-Tokamak approach using a field-reversed configuration. The company has announced agreements to provide fusion power to data centers by the late 2020s, an ambitious timeline that has drawn both excitement and skepticism. Whether these private ventures can deliver on their promises remains to be seen, but their presence has injected urgency and competition into the field. Cost estimates for fusion electricity vary. Some analyses suggest that fusion could produce power at 5 to 10 cents per kilowatt-hour, comparable to wind and solar with storage, if capital costs can be controlled and if capacity factors, the fraction of time the plant operates, are high. Fusion plants, like fission plants, could operate continuously, providing baseload power, a valuable attribute in a grid increasingly dominated by intermittent renewables. However, achieving low costs requires solving numerous problems. The neutron damage to materials limits component lifetimes, necessitating periodic replacement of the first wall, blanket, and diverter. These replacements are expensive and result in downtime. If a reactor must shut down for months every few years to replace irradiated components, its capacity factor drops and its effective cost per kilowatt-hour rises. Manufacturing tritium within the reactor, rather than purchasing it externally, is essential for economic viability. Tritium is expensive and scarce. A fusion plant that relies on external tritium supplies would face prohibitive fuel costs. Breeding tritium in situ from lithium is the only practical approach, but ensuring a breeding ratio consistently above 1, accounting for losses and uncertainties, is a technical challenge with direct economic consequences. The fuel itself, deuterium and lithium, is inexpensive and abundant. Deuterium can be extracted from seawater at low cost. Lithium is widely available, used currently in batteries and other applications. The fuel cost for fusion would be negligible, a major advantage over fossil fuels. However, the capital cost of the reactor dominates the economics. If the reactor is too expensive to build, cheap fuel provides little consolation. Fusion reactors are complex machines, likely more complex than fission reactors. Complexity drives cost. It also affects reliability. More components, more systems, more potential failure modes. Operating a fusion plant will require skilled personnel, sophisticated diagnostics, and robust maintenance protocols. These operational costs must be factored into the overall economics. Licensing and regulation add another layer. No regulatory framework for commercial fusion plants currently exists, though agencies in the United States, the United Kingdom, and elsewhere are beginning to develop one. Fusion plants will need to demonstrate safety, manage radioactive materials, and protect workers and the public. The licensing process for fission plants is lengthy and expensive. Fusion may benefit from a less burdensome process, given the absence of chain reactions and lower long-term waste, but regulatory approval will still require extensive documentation and testing. Public acceptance is also a factor. Fusion has generally enjoyed a more favorable public image than fission, perceived as cleaner and safer. However, any technology involving radioactivity and high-energy processes will face scrutiny. Transparent communication, rigorous safety standards, and demonstrated reliability will be necessary to build public trust. Some proponents argue that fusion should not be judged solely on economic competitiveness with existing technologies. They point to its potential to provide abundant, clean energy in a world facing climate change and growing energy demand. If fusion can contribute to decarbonization, stabilize energy prices, and reduce geopolitical tensions over energy resources, it may be worth public investment even if it is not the cheapest option. Others are less sanguine, arguing that resources devoted to fusion might be better spent on scaling up renewables, improving energy storage, or developing advanced fission reactors. The debate is pragmatic and ongoing, reflecting different views on risk, timelines, and the value of technological diversity in the energy portfolio. China's investment in fusion reflects a strategic calculation. The country has committed substantial resources to multiple fusion projects, viewing energy security and technological leadership as national priorities. East, HL2M, and other Chinese tokamaks are part of a long-term effort to ensure that when fusion becomes viable, China will have the expertise and infrastructure to deploy it at scale. This approach is patient, state-driven, and less concerned with near-term profitability than with long-term capability. The United States and Europe have historically led fusion research, but their funding has fluctuated with political priorities and budget constraints. Private investment has partly filled the gap, bringing new energy and capital, but also introducing commercial pressures and shorter timelines that may or may not align with the fundamental challenges of fusion. International collaboration, exemplified by ITER, spreads costs and risks but also complicates decision-making and slows progress. National programs can move faster but lack the resources and knowledge base of a global effort. The balance between collaboration and competition, between public and private, between caution and ambition, shapes the trajectory of fusion development. Ultimately, the economics of fusion will be determined not by projections and models but by actual plants, built and operated, producing electricity at a known cost. Until that happens, the debate will continue, informed by each new experiment, each technological advance, and each shift in the broader energy landscape. As we look ahead to the societal implications of fusion, should it succeed, we must consider not just the machines and the money but the world they might create, a world where energy is abundant, where the threat of climate change is diminished, and where new questions, new challenges, and new possibilities emerge. Part 7. The Neutron Problem and Material Frontiers. Return, for a moment, to the neutron. It is both the gift and the curse of deuterium-tritium fusion. The neutron carries energy outward from the plasma, energy that must be harvested if fusion is to generate power. But the neutron also inflicts damage, relentless and cumulative, on every material it encounters. Understanding this damage, mitigating it, and designing materials that can endure it are among the most critical challenges facing fusion energy. When a 14 million electron-volt neutron strikes an atom in the reactor's structural steel or tungsten armor, it transfers energy through collision. If the collision is energetic enough, the struck atom is knocked entirely out of its position in the crystal lattice, creating a vacancy where the atom once sat and an interstitial atom lodged awkwardly between lattice sites. This displacement is the beginning of a cascade. The displaced atom may strike other atoms, displacing them in turn, creating a cluster of defects. Over time, these defects accumulate. Vacancies cluster together, forming voids. Interstitial atoms migrate and aggregate, causing the material to swell. Grain boundaries, the interfaces between crystalline regions in a metal, become decorated with defects and embrittled. The material's strength decreases, its ductility vanishes, and it becomes prone to sudden fracture. In severe cases, dimensional changes occur, swelling or shrinking by several percent, enough to distort components and compromise structural integrity. The total neutron exposure a material receives is measured in displacements per atom, or dP. A commercial fusion reactor's first wall might accumulate 50 to 100 dPa over several years of operation, far exceeding the experience base from fission reactors. At such levels, even well-understood materials behave unpredictably. Extrapolating from lower-dose data is risky. Direct testing at fusion-relevant doses is essential, but difficult. Existing neutron sources cannot fully replicate fusion conditions. Fission reactors produce neutrons, but most are at lower energies. Spallation sources, where high-energy protons strike a heavy metal target to release neutrons, come closer but still differ in spectrum and flux. A fusion-relevant neutron source, perhaps a small DT burning device optimized for materials testing rather than power production, has been proposed but not yet built. Japan's International Fusion Materials Irradiation Facility, or IFMIF, was planned for this purpose but has faced funding and political challenges. A successor concept, the IFMIF Doness facility, is being developed in Europe, aiming to provide a partial solution. Materials development is not simply about surviving neutron damage. The materials must also perform their functions. Plasma-facing components must withstand not only neutrons but also intense heat, plasma bombardment, and erosion. Tungsten is the leading candidate for diverter surfaces. It has the highest melting point of any metal, over 3,400 degrees Celsius, and low sputtering yield, meaning plasma ions dislodge relatively few tungsten atoms when they strike. But tungsten is brittle at room temperature and becomes even more brittle after neutron irradiation. It can develop cracks under thermal cycling, where repeated heating and cooling induce stress. Tungsten also interacts with hydrogen isotopes, absorbing them and forming bubbles that can blister and exfoliate the surface. Managing these effects requires careful control of operating temperature, surface engineering, and possibly the use of tungsten alloys or composites. Liquid metals offer an intriguing alternative. Lithium, flowing as a liquid at a few hundred degrees Celsius, could serve as both a plasma-facing surface and a breeding blanket for tritium. Liquid surfaces cannot crack or erode in the conventional sense. They are self-healing. If disturbed, they simply flow back into place. However, liquid metals introduce their own complications. Lithium is highly reactive, corroding many structural materials. Containing and circulating it safely, especially in a magnetic field which induces complex magnetohydrodynamic flows, is challenging. China's East Tokamak has conducted experiments with liquid lithium limiters, where a slowly flowing lithium surface interacts with the plasma edge. Results have shown improved plasma performance in some regimes, reduced impurity contamination, and hints that liquid lithium might help manage heat exhaust. These are early-stage experiments, far from the demonstration of a full liquid metal plasma-facing system, but they illustrate the exploratory nature of fusion materials research. Breeding tritium from lithium requires materials that can both absorb neutrons and release tritium efficiently. Solid ceramic breeders, such as lithium orthosilicate or lithium metadidenate, are chemically stable and can be fabricated into pebbles or blocks that pack into breeding blankets. Neutrons interact with lithium-6, a naturally occurring isotope comprising about 7% of natural lithium, producing tritium and helium. The tritium must then diffuse out of the ceramic grains through interconnected porosity and into a purge gas stream that carries it to recovery systems. This process is temperature dependent. Too cold, and the tritium release is slow, leading to buildup and potential retention. Too hot, and the ceramic may sinter, closing pores and trapping tritium. Operating within the narrow temperature window that balances tritium release, structural integrity, and compatibility with coolant materials is a delicate optimization. Liquid breeders, like lithium lead eutectic alloys, eliminate the tritium release problem. The tritium dissolves in the liquid metal and can be extracted continuously as the coolant circulates. Liquid breeders also provide excellent neutron multiplication, where neutrons induce secondary reactions that produce additional neutrons, improving the overall tritium breeding ratio. However, liquid metals are corrosive and challenging to handle. They require compatible structural materials, careful chemistry control, and robust pumping systems. Neutron shielding is essential to protect the superconducting magnets. These magnets, operating at cryogenic temperatures, are sensitive to radiation. Even modest heating from neutron absorption can disrupt superconductivity, causing a quench. Shielding typically consists of layers of materials chosen to absorb and moderate neutrons. Steel, boron carbide, and water or other hydrogenous materials are common choices. The shield must be thick enough to reduce neutron flux to acceptable levels, but not so thick that it makes the reactor prohibitively large and expensive. Designing effective shielding is a complex neutronics problem, requiring detailed simulations to track neutrons as they scatter, are absorbed, and undergo secondary reactions. Uncertainties in nuclear cross-section data, particularly for 14 million electron-volt neutrons, add margins of error to these calculations. Experimental validation, ideally in a real fusion environment, is necessary to confirm that the shield performs as designed. Beyond the first wall, blanket, and shield, other materials face less severe but still significant neutron exposure. Cooling pipes, structural supports, diagnostic windows, and instrumentation all accumulate damage over the reactor's lifetime. Maintaining the integrity of these components, many of which are inaccessible once the reactor is operational, requires conservative design margins and careful monitoring. Remote maintenance and repair systems must handle components that are not only radioactive but also physically large, hot, and geometrically complex. Manipulators and cutting tools must operate reliably in confined spaces, under time pressure, with no margin for error. ITER is developing and testing these systems now, but the demands on a commercial reactor operating for decades will be greater. Material activation, the production of radioactive isotopes when stable materials absorb neutrons, determines the long-term waste burden of fusion. Unlike fission, fusion does not produce transuranics or long-lived fission products, but neutron activation still generates radioactive waste. The choice of structural materials affects the waste problem significantly. Reduced activation ferritic martensitic steels, as mentioned earlier, are designed to minimize long-lived isotopes. Elements like molybdenum, niobium, and nickel, which produce problematic activation products, are replaced with tungsten, tantalum, and manganese. The result is a steel that, after several decades of decay, becomes low-level waste that can be recycled or disposed of more easily than conventional stainless steels. Vanadium alloys are another candidate, offering even lower activation, but vanadium is expensive and its alloys less well characterized. Silicon carbide composites, developed for aerospace and nuclear applications, are also being investigated for fusion. They offer low activation, high temperature strength, and resistance to neutron damage, but they are brittle and challenging to manufacture in complex shapes. The interplay between materials science, neutronics, thermal hydraulics, and structural mechanics defines the material frontier of fusion. Each design choice, each alloy composition, each geometric detail affects performance, cost, safety, and feasibility. There is no perfect material, only trade-offs and compromises, informed by experiment, analysis, and judgment. As materials research advances, computational tools play an ever larger role. Molecular dynamics simulations model atomic scale processes, predicting how defects form and evolve. Continuum models simulate the behavior of components under operational stresses. Machine learning algorithms search vast parameter spaces for promising alloy compositions or fabrication techniques. These tools accelerate discovery but cannot replace physical testing. The final arbiter is always the experiment, the material subjected to actual fusion conditions and examined for damage. The neutron problem is not insurmountable, but it is persistent, demanding ingenuity, resources, and time. Solving it is prerequisite to commercial fusion. As we turn next to the systems that extract and convert fusion energy into electricity, we will see how materials challenges intertwine with every other aspect of reactor design. Part 8: Heat, Power, and the Balance of Plant. A fusion reactor is not merely a plasma chamber and magnets. It is a thermal power plant, a complex system designed to extract heat from fusion reactions, convert it to electricity, and manage all the supporting processes required for safe, continuous operation. This broader system, everything beyond the fusion core itself, is called the balance of plant, and its performance determines whether fusion can be economically and practically viable. Begin with heat extraction. The neutrons from DT fusion deposit their energy in the blanket, heating the coolant flowing through it. This coolant, whether water, helium, or liquid metal, circulates in a closed loop, carrying heat to a heat exchanger where it transfers thermal energy to a secondary working fluid. That working fluid, often water or a gas, drives a turbine, which spins a generator, producing electricity. This is fundamentally the same process used in coal, natural gas, or fission power plants. The Rankine cycle for steam turbines or the Brayton cycle for gas turbines convert thermal energy to mechanical work, subject to the same thermodynamic limits. Efficiency depends on the temperature difference between the hot and cold reservoirs. Higher coolant temperatures yield higher efficiency, but also impose greater stress on materials. Fusion offers the possibility of high-temperature operation. If blanket materials can withstand it, coolant outlet temperatures of 600 to 800 degrees Celsius or higher might be achievable, enabling thermal-to-electric conversion efficiencies approaching 45 or 50%. This compares favorably with light water fission reactors, which operate cooler and achieve efficiencies around 33%. Helium coolant is attractive for its chemical inertness and neutron transparency. It does not absorb neutrons significantly, leaving more available for tritium breeding. Helium also does not become radioactive when irradiated. It can be heated to high temperatures without phase change or chemical reaction. However, helium has low heat capacity, requiring large flow rates and high pressures, typically several megapascals, to extract sufficient heat. This demands robust piping, heat exchangers, and circulators, adding to system complexity. Water coolant is well understood from decades of fission reactor experience. It provides excellent heat transfer and is relatively inexpensive. Pressurized water systems operate at several hundred degrees Celsius, delivering moderate conversion efficiency. However, water activates under neutron irradiation, producing oxygen-16 and tritium, the latter being a concern for contamination and environmental release. Managing tritium in the coolant loop, preventing leaks, and ensuring that tritium does not escape into the environment requires careful design and monitoring. Liquid metal coolants, such as lithium lead or sodium, offer high heat capacity, low pressure operation, and the potential to combine cooling with tritium breeding. They can operate at high temperatures, enabling high efficiency. Liquid metals also exhibit favorable safety characteristics, remaining liquid over a wide temperature range and having high boiling points. However, they are chemically reactive, corrosive to many structural materials, and opaque, making inspection difficult. Leaks can be hazardous, and the magnetohydrodynamic effects of flowing liquid metal in strong magnetic fields must be carefully managed. The choice of coolant ripples through the entire design. It affects material selection, component layout, safety systems, and operational procedures. It also influences tritium management. Tritium, being chemically identical to hydrogen, can permeate through hot metal walls, entering the coolant loop. If the coolant is water destined for a steam turbine, tritium contamination is a serious concern. Barriers and getters, materials that preferentially absorb tritium, must be installed to limit permeation. Tritium extraction from the breeding blanket is a continuous process. As tritium is produced by neutron interactions with lithium, it must be removed to prevent buildup, which could degrade breeding performance or create safety hazards. In solid breeder blankets, a purge gas, often helium mixed with a small amount of hydrogen, flows through the pebble bed, sweeping out tritium. The gas then passes through a processing system where tritium is separated, purified, and stored for reinjection into the plasma. In liquid breeder blankets, tritium dissolves in the molten metal. Extraction typically involves exposing the liquid to a vacuum or a carrier gas, allowing tritium to evaporate or deorb. This process must be efficient and continuous, operating alongside heat extraction without significant energy penalty. Tritium handling systems must meet stringent safety standards. Tritium is radioactive, though weakly so. It emits low-energy beta particles that are stopped by skin or a thin barrier, posing minimal external hazard. However, if tritium is inhaled or ingested, it can be absorbed into body tissues, where it continues to emit radiation. Preventing tritium release, detecting leaks promptly, and maintaining low occupational and public doses are regulatory requirements and ethical obligations. Modern tritium handling systems use multiple containment barriers, continuous monitoring, and automated controls to minimize risk. Glove boxes, hermetically sealed rooms, and remote handling reduce worker exposure. Tritium inventory is tracked precisely, both for safety and for fuel accounting. Losses to the environment are kept well below regulatory limits through careful engineering and operational discipline. Power conversion efficiency matters not just for economics but also for heat rejection. A 50% efficient power plant converts half the fusion energy to electricity and rejects the other half as waste heat. This waste heat must be dissipated to the environment, typically through cooling towers or other heat rejection systems. Lower efficiency means more waste heat, larger cooling systems, and greater environmental impact. Grid integration introduces additional considerations. Fusion plants, like fission plants, are best suited for baseload operation, running continuously at steady power. Ramping power up and down, load following, is possible but complicates plasma control and thermal management. In an electricity grid increasingly dominated by variable renewables like wind and solar, baseload power is valuable for stability, but markets and grid operators may also demand flexibility. Energy storage, either on-site or grid-scale, could help bridge this gap. A fusion plant might operate continuously, storing excess electricity in batteries or producing hydrogen when demand is low, and drawing on those reserves when demand peaks. This adds cost and complexity but enhances the plant's role in a decarbonized energy system. Auxiliary systems consume significant power. The magnets, though superconducting, require refrigeration systems to maintain cryogenic temperatures. Plasma heating systems, whether radiofrequency antennas or neutral beam injectors, draw many megawatts. Cooling pumps, tritium processing, control systems, and diagnostics all require electricity. In a net energy-producing reactor, these systems are powered by the plant's own output, but they reduce the net electricity available for the grid. The balance between gross fusion power, auxiliary power consumption, conversion efficiency, and grid delivery is the essence of the energy balance problem. A reactor might achieve a plasma Q of 10, producing 10 times more fusion power than input heating power, but if auxiliary systems consume additional power and conversion efficiency is only 40%, the net electricity gain is smaller than it first appears. Optimizing this balance is crucial for economic viability. Reliability and uptime are equally important. A reactor that must shut down frequently for maintenance or repairs, even if technically successful, will struggle to compete economically. Scheduled outages for component replacement, refueling, and inspection must be minimized and carefully planned. Unscheduled outages, caused by equipment failure or operational issues, must be rare. Achieving high reliability requires robust design, extensive testing, and operational experience, none of which exist yet for fusion. Early plants will likely experience lower availability as issues are discovered and resolved. Learning curves will be steep. The path from demonstration to mature, reliable operation may take decades, as it did for fission. China's approach to fusion development emphasizes not just scientific milestones but also engineering readiness and operational experience. Facilities like EAST are used not only for plasma physics experiments but also for testing subsystems, training personnel, and developing operational protocols. This systems-level focus reflects an understanding that fusion success depends on integrating many complex components into a functioning whole. Private fusion companies, driven by investor timelines and commercial pressures, are exploring modular designs, factory fabrication, and rapid construction to reduce costs and accelerate deployment. Smaller reactors, potentially mass-produced, might achieve economies of scale and learning efficiencies faster than one-off, bespoke designs. Whether this approach can overcome the fundamental challenges of fusion remains uncertain, but it represents a different philosophy, one prioritizing speed and iteration over cautious, incremental progress. As we move forward to consider the societal, political, and ethical dimensions of fusion, we carry with us the understanding that fusion is not just a physics problem or an engineering problem, but a systems problem, demanding integration, balance, and relentless attention to detail across every domain. Part 9. The timeline question and the patience of decades. Fusion has been perpetually 30 years away for the past 70 years. This joke, repeated wearily in the fusion community, captures both the frustration and the stubborn optimism that characterizes the field. Predictions made in the 1950s suggested fusion power by the 1980s. Those made in the 1980s pushed the date to the early 21st century. Today, most projections place commercial fusion somewhere in the 2040s or 2050s, though some private companies claim earlier timelines. Why has fusion taken so long? The question invites multiple answers, some technical, some institutional, some simply reflective of the profound difficulty of the task. Early optimism was based on incomplete understanding. Plasma physics is subtle. Instabilities and turbulence that seemed manageable on paper proved intractable in practice. Each solution revealed new problems. Confinement improved, but energy losses through turbulent transport remained stubbornly high. Heating methods advanced, but controlling plasma impurities required decades of refinement. Funding has also been inconsistent. Fusion research is expensive, requiring large facilities, specialized equipment, and sustained investment over many years. In the United States, fusion funding peaked in the late 1970s and has remained relatively flat in real terms since then. Europe and Japan have maintained steadier support, and China has ramped up investment significantly in recent decades, but no nation has committed the resources that a crash program, comparable to the Apollo moon landing, would require. ITER embodies the international collaboration model, spreading costs but also distributing decision-making across many governments with different priorities. This structure has strengths, ensuring broad buy-in and shared expertise, but it also slows progress. Design changes require consensus. Procurement involves multiple suppliers across different countries, each with their own regulations and timelines. Delays compound. What was once envisioned as a project completed by 2020 has stretched into the 2030s. Yet ITER is not a failure. It is a bet on long-term success, a machine designed to prove that net energy gain is achievable at a scale relevant for power production. If ITER succeeds, it will validate the physics, the engineering, and the materials that underpin Tokamak fusion. That validation is worth the wait, or so the argument goes, because the prize is a technology that could provide energy for centuries. Demo, the demonstration power plant that would follow ITER, is itself a multi-decade project. Europe's conceptual demo designs envision a machine that would begin construction in the late 2030s or early 2040s, with first electricity production perhaps in the 2050s. China has announced plans for its own fusion demonstration reactor, sometimes called CFETR, aiming for operation potentially in the 2030s or 2040s, though these timelines are ambitious and subject to change. These are long-term projects, generational commitments, beyond the horizon of most political cycles or corporate planning. Private companies offer a contrasting approach. They argue that smaller, faster, more agile development can accelerate fusion. Commonwealth Fusion Systems aims for net energy gain with spark in the mid-2020s and a pilot plant producing electricity to the grid by the early 2030s. Helion has claimed even faster timelines, targeting commercial operation by the late 2020s. TE Technologies pursues advanced fusion fuels like proton-boron, which would eliminate neutron damage problems but require far higher temperatures, with its own multi-decade roadmap. Skepticism about these timelines is warranted. Fusion has a history of overpromising. Private companies, eager to attract investment and meet investor expectations, may underestimate the challenges. On the other hand, private ventures bring fresh capital, new ideas, and a willingness to take risks that publicly funded programs often avoid. They accelerate certain technological developments, particularly in magnets, materials, and computational design. High-temperature superconductors, for instance, have matured rapidly in recent years, driven partly by fusion applications. Repco tapes are now commercially available, and companies are learning to manufacture them at scale and integrate them into large magnet systems. This progress benefits the entire field, whether the magnets are used in spark, ITER, or future devices. Another factor affecting timelines is the learning process. Fusion is not one problem but many. Each reactor component, each subsystem, each operational regime must be understood, tested, and optimized. Knowledge accumulates slowly. A breakthrough in one area, say plasma confinement, does not automatically solve problems in another, such as tritium breeding or remote maintenance. The system must come together as a whole, and that integration takes time. Comparisons to other large technological endeavors offer perspective. The Manhattan Project, developing nuclear fission weapons, took roughly 5 years under wartime urgency and virtually unlimited resources. Commercial fission power took another decade beyond that to mature. The Apollo program, similarly driven by geopolitical competition and generous funding, landed humans on the moon in less than a decade. Fusion has not enjoyed such focus or resources. It has proceeded more like the development of aviation or computing, a long arc of incremental improvement punctuated by occasional leaps. Some argue that fusion should be treated as a long-term research program rather than an imminent energy solution. Its value lies not in meeting near-term climate goals but in providing a future option, a backstop technology for the second half of the century and beyond. By this logic, steady investment, patient development, and rigorous validation are appropriate, even if they mean waiting decades for commercial deployment. Others contend that this patience is a luxury we cannot afford. Climate change is accelerating. Energy demand in developing nations is rising. We need solutions now, or at least within the next decade or two. Fusion, perpetually on the horizon, distracts from deploying existing low-carbon technologies like wind, solar, batteries, and advanced fission. Resources devoted to fusion might yield greater near-term impact if redirected. The debate is pragmatic and philosophical. It hinges on views about risk, technological uncertainty, and the appropriate portfolio of energy investments. Fusion advocates argue for maintaining diverse options, hedging against the possibility that renewables alone may not suffice. Critics counter that fusion's persistent delays and technical hurdles make it an unreliable bet. China's strategy appears to embrace both positions. The nation invests heavily in renewables, building vast solar and wind farms, while also pursuing fusion, advanced fission, and other long-term technologies. This broad portfolio reflects a large, growing economy with diverse energy needs and a planning horizon that extends decades into the future. China views energy dominance, both in deployment and in technology development, as strategic, and fusion is part of that calculus. Public perception of fusion timelines has shifted over the years. Early enthusiasm, fueled by mid-century optimism about nuclear technology, gave way to skepticism as deadlines passed unmet. More recently, the NIF ignition breakthrough and the influx of private investment have rekindled interest. Media coverage has increased. Policymakers are paying attention. Whether this translates to sustained support, public or private, depends on continued progress and clear communication about what fusion can and cannot achieve. Fusion researchers have learned, sometimes painfully, the importance of managing expectations. Overpromising erodes credibility. Underpromising may fail to inspire. The balance is delicate. Most fusion scientists today speak cautiously, emphasizing progress while acknowledging uncertainties. They avoid firm predictions, preferring conditional statements. If funding continues, if technical milestones are met, if no unforeseen obstacles arise, then commercial fusion might be achieved within a certain time frame. This caution reflects hard-won wisdom. It also reflects the reality that fusion is genuinely difficult, that no one knows for certain how long it will take, and that honesty, even when it disappoints, is better than false hope. As we consider the geopolitical and societal implications of fusion, we must hold this timeline uncertainty in mind. Fusion may arrive in 20 years, or 40, or not at all. The world will continue to evolve in the meantime, and the context into which fusion emerges, if it does, will shape how it is received and what role it plays. Part 10: Geopolitics, Energy Security, and the Global Fusion Race. Energy has always been intertwined with power, not merely electrical power but political, economic, and military power. Nations that control energy resources wield influence. Those that depend on imports face vulnerability. The shift from coal to oil reshaped global politics in the 20th century. The rise of renewables is reshaping it again in the 21st. Fusion, should it succeed, would introduce yet another transformation, one with implications that ripple across geopolitics, trade, security, and international relations. Consider energy independence. A nation with abundant fusion power would no longer need to import fossil fuels. It could generate electricity, produce hydrogen for transportation and industry, and power desalination plants to address water scarcity, all using domestically available fuel. Deuterium is present in any nation's seawater. Lithium, needed for tritium breeding, is widely distributed, though not uniformly. A world where many nations possess fusion technology is a world where energy leverage shifts away from oil and gas exporters. This prospect alarms some and excites others. For nations like Saudi Arabia, Russia, or Venezuela, whose economies depend heavily on hydrocarbon exports, fusion represents a long-term threat. If demand for oil and gas declines because fusion and renewables provide cheaper, cleaner alternatives, these nations face economic and political upheaval. The petrostates of the Middle East are already diversifying, investing in renewables, sovereign wealth funds, and other industries, preparing for a post-oil future that may or may not include fusion. For nations like Japan, South Korea, or much of Europe, which import most of their energy, fusion offers the promise of security and self-sufficiency. Japan, still grappling with the aftermath of the Fukushima disaster and the shutdown of much of its nuclear fleet, has maintained strong support for fusion research. The country participates in ITER and operates the JT-60SA Tokamak, a collaborative project with Europe. Fusion aligns with Japan's goals of energy security, technological leadership, and climate action. China's fusion ambitions are explicit and strategic. The government has invested billions in fusion research, built multiple large experimental facilities, and set ambitious timelines for demonstration reactors. China views fusion as part of its broader energy strategy, complementing renewables, fission, and efficiency improvements. Fusion also represents a domain where China can achieve parity or leadership, demonstrating scientific and technological prowess on the global stage. The international race in fusion is both cooperative and competitive. ITER exemplifies cooperation, bringing together nations that are often geopolitical rivals. The project continues despite tensions between Russia and the West, between China and the United States. Scientists and engineers from these nations work side by side, sharing data and expertise. This collaboration is fragile, subject to political currents, but it endures because the goal transcends national interests, or at least it is framed that way. Yet competition persists. Nations and private companies seek to be first, to claim the prestige and potential economic advantages of fusion success. Patent filings, export controls on critical technologies, and restrictions on knowledge sharing reflect the competitive dimension. High-temperature superconductors, advanced manufacturing techniques, and tritium handling expertise are strategic assets. Those who control them may shape the fusion industry's future. The United States, historically a leader in fusion research, has seen its relative position erode as funding stagnated and other nations ramped up investment. Recent policy attention, spurred by the NIF ignition result and private sector activity, has led to increased funding and policy initiatives aimed at regaining leadership. The Department of Energy has launched programs to support fusion development, and legislation has been proposed to streamline regulatory pathways for fusion energy. Europe, through the European Union and individual nations, continues to invest heavily, anchored by ITER and national programs in France, Germany, the United Kingdom, and elsewhere. Brexit complicated the UK's participation in EU fusion programs, but the country has sought to maintain its role and has supported private fusion ventures like Tokamak Energy and First Light Fusion. Smaller nations also participate, contributing expertise in specialized areas. South Korea, a partner in ITER, operates the KSTR Tokamak, which has achieved record-setting long-pulse high-performance plasmas. India, another ITER partner, is developing its own fusion program. These countries view fusion as an opportunity to build scientific capacity, train researchers, and participate in a technology that may define future energy systems. The potential for fusion to alter global power dynamics extends beyond energy independence. Fusion could enable energy-intensive industries to relocate, decoupling industrial production from proximity to cheap fossil fuels. It could power carbon capture and sequestration at scales currently impractical, or support massive desalination and water transport projects in arid regions. It could make space exploration more feasible, providing propulsion or power for long-duration missions. These possibilities are speculative, dependent on fusion's success and on economic competitiveness. But they illustrate why nations invest in fusion despite the uncertainties. The upside, if realized, is transformative. The downside of not investing is potentially being left behind, dependent on others for a critical technology. Fusion also intersects with nuclear weapons policy. The science and technology of fusion have dual-use potential. While fusion reactors are not weapons, and the path from reactor to bomb is neither simple nor direct, knowledge gained in fusion research can inform weapons design and maintenance. The NIF facility, for instance, was built primarily for stockpile stewardship, studying nuclear weapons physics without explosive testing. Its fusion ignition achievement serves both energy research and national security objectives. This dual-use nature complicates international collaboration and non-proliferation efforts. Sharing detailed fusion research might inadvertently aid weapons programs. Restrictions on sharing, however, slow scientific progress and breed mistrust. Navigating this tension requires careful diplomacy, transparency where possible, and red lines where necessary. Fusion governance, the rules and institutions that would regulate a future fusion industry, is still in its infancy. Unlike fission, which has decades of regulatory precedent and international treaties, fusion lacks established frameworks. The International Atomic Energy Agency, or IAEA, has begun to consider fusion, but its primary focus remains fission and weapons proliferation. National regulatory agencies, such as the Nuclear Regulatory Commission in the United States, are developing approaches to fusion licensing, often treating it differently from fission due to its distinct safety profile. As fusion transitions from research to deployment, governance questions will intensify. Who sets safety standards? How is tritium handled and accounted for? What happens if a fusion plant in one country experiences an accident with cross-border impacts? How are fusion materials, some of which could be radioactive or have weapons relevance, controlled in international trade? These questions do not have simple answers. They require international dialogue, technical expertise, and political will. The fusion community, aware of these challenges, has begun to engage policymakers, but much work remains. Public opinion and social acceptance will also shape fusion's geopolitical role. A technology perceived as safe, clean, and beneficial will spread more easily than one viewed with suspicion or fear. Fusion benefits from a relatively positive public image compared to fission, but it is not immune to opposition. Concerns about radioactivity, cost, and the wisdom of continued reliance on centralized, high-technology energy systems may arise, particularly if fusion's deployment coincides with successful scaling of decentralized renewables. Environmental and social justice considerations matter. Large fusion plants, like large fission or fossil plants, require significant land, water for cooling, and transmission infrastructure. Siting them near population centers raises concerns about safety and equity. Ensuring that fusion benefits are widely shared rather than accruing only to wealthy nations or corporations will require deliberate policy choices. Fusion, if it arrives, will not emerge into a static world. It will interact with ongoing trends, the growth of renewables, the electrification of transport, the rise of artificial intelligence and its energy demands, shifting demographics, and climate impacts already underway. The world that fusion enters will shape what fusion becomes, and fusion, in turn, will shape that world. As we move toward imagining what daily life might look like in a fusion-powered future, we carry with us the understanding that fusion is not merely a technical achievement but a profoundly human endeavor, shaped by politics, economics, values, and choices. Part 11. Imagining the fusion future. Imagine a morning, decades from now, in a world where fusion has succeeded. You wake in a home heated and cooled efficiently, powered by a grid that hums with steady, abundant electricity. The air outside is cleaner than it was in your grandparents' time. Carbon emissions have fallen, not because humanity has learned to do without energy, but because energy has been decoupled from carbon. Fusion plants, scattered across continents, burn fuel drawn from seawater and lithium, producing helium and heat and the electricity that runs through every wire in every wall. This is not utopia. The world still faces challenges, inequalities, conflicts. But the energy constraint has loosened. Industries that once burned coal or gas now draw power from fusion and renewables. Electric vehicles charge overnight without straining the grid. Desalination plants turn seawater into fresh water for agriculture and cities in arid regions. Vertical farms, lit by fusion-powered LEDs, grow food year-round in urban centers. Hydrogen, produced by electrolysis using fusion electricity, fuels ships and aircraft and industrial processes that cannot easily electrify. The transition was neither smooth nor immediate. The first commercial fusion plants were expensive, financed by governments and international consortia willing to bear the risk. They experienced outages, component failures, learning curves steep and costly. Engineers worked through problems that had not appeared in experimental reactors. Materials failed in unexpected ways. Tritium systems leaked. Divertors eroded faster than models predicted. Each problem was solved, slowly, through iteration and ingenuity. Over time, as more plants were built, costs declined. Manufacturing scaled up. Supply chains matured. Standardized designs replaced bespoke prototypes. The second generation of fusion plants was smaller, more reliable, cheaper to build. Private companies entered the market, competing on efficiency and innovation. Some designs succeeded, others failed, their investors absorbing losses, their lessons informing future attempts. Not every nation adopted fusion at the same pace. Wealthy countries with capital and technical capacity built plants first. Poorer nations, still developing their grids and infrastructure, continued to rely on a mix of renewables, natural gas, and older technologies. International finance mechanisms, climate funds, and technology transfer agreements helped bridge the gap, but disparities persisted. Energy access improved globally, but the benefits of fusion were unevenly distributed, reflecting broader inequalities. Geopolitics shifted subtly. Oil exporters, having diversified over decades, remained influential but less dominant. Energy trade patterns changed. Lithium, once a commodity for batteries, became strategic for fusion tritium breeding. Nations with lithium reserves negotiated favorable terms. Others developed recycling and extraction technologies to minimize dependence. The competition for resources did not disappear, it simply took new forms. Climate impacts, though mitigated by the shift away from fossil fuels, were not reversed. Decades of emissions had already set changes in motion. Sea levels rose. Weather patterns shifted. Ecosystems adapted or perished. Fusion helped limit further warming, buying time for carbon removal efforts and adaptation, but it was not a panacea. The past could not be undone, only the future shaped differently. Public perception of fusion evolved. Early skepticism, rooted in memories of nuclear accidents and broken promises, gave way to cautious acceptance as plants operated safely and reliably. Transparency helped. Regulators published safety records. Communities near fusion plants saw economic benefits, jobs, and tax revenue without the pollution of coal or the long-term waste concerns of fission. Trust was built slowly, through performance and openness. Education systems adapted. Fusion's success created demand for specialists, plasma physicists, nuclear engineers, materials scientists. Universities expanded programs. Apprenticeships trained technicians to maintain and operate fusion plants. A generation grew up knowing fusion not as a dream but as infrastructure, as ordinary as wind turbines or solar panels, part of the landscape of daily life. The environmental footprint of fusion was real but manageable. Plants required cooling water, though closed-loop systems minimized consumption. They produced low-level radioactive waste from activated materials, stored on-site or in regional facilities, decaying to safe levels over decades rather than millennia. The waste problem was smaller than fission, larger than renewables, an acceptable trade-off in the broader energy mix. Fusion did not displace renewables. Instead, the two coexisted. Solar and wind provided cheap, variable power. Fusion provided steady baseload, complementing renewables and filling gaps when the sun did not shine and the wind did not blow. Energy storage, in batteries and hydrogen and other forms, smoothed the transitions. Grids became smarter, more flexible, integrating diverse sources seamlessly. The fusion future was not one of infinite, costless energy. Physics and economics imposed limits. Fusion electricity was affordable but not free. Conservation and efficiency still mattered. Demand grew, but so did awareness of limits, of the need to balance consumption with sustainability. Fusion enabled a higher standard of living for more people, but it did not erase the need for choices, for wisdom in how energy was used. Space exploration benefited. Fusion propulsion concepts, long theoretical, became feasible with mature terrestrial fusion technology. Spacecraft powered by fusion engines could reach Mars in weeks rather than months, could venture to the outer planets and beyond. Space-based fusion reactors, free from gravity's constraints, offered possibilities for settlements on the Moon or Mars. These were distant prospects, but fusion's success on Earth made them imaginable. Industrial processes transformed. Energy-intensive industries, steel-making, chemical production, cement manufacturing, adopted fusion power where it made economic sense. Some processes shifted to hydrogen reduction, using fusion-derived hydrogen instead of coal. Recycling became more viable as the energy cost of processing scrap declined. The circular economy, long advocated, found firmer footing in an energy-abundant world. The fusion future was ordinary in the way successful technologies become ordinary. Few people thought about the physics when they flipped a light switch, just as few today think about electromagnetism when they use a smartphone. Fusion receded into the background, reliable and unremarkable, infrastructure that simply worked. Yet it was also extraordinary. The ability to mimic stars, to harness the power that lights the cosmos, remained a source of quiet wonder. School children toured fusion plants and learned that humans had achieved something audacious, that persistence and ingenuity had overcome obstacles once thought insurmountable. The story of fusion became a story about what is possible when we commit to long-term goals, when we invest in knowledge, when we refuse to accept limits as final. This imagined future is not guaranteed. It rests on choices made now, on funding decisions, on political will, on scientific breakthroughs that may or may not come. But it is plausible, grounded in physics we understand and engineering we are learning. It is a future worth reaching for, not because it is certain, but because the effort to reach it teaches us, advances us, and prepares us for whatever future actually unfolds. As we approach the close of this narrative, we carry the image of that possible morning, that world where fusion has found its place, alongside all the complexity, nuance, and challenge that brought it there. Part 12. the quiet fire and the long dream. We have wandered far, through physics and engineering, through politics and economics, through materials tested to destruction and plasmas hotter than stars. We have traced the history of fusion research, its setbacks and milestones, its audacious ambitions and grinding realities. We have imagined futures, some hopeful, some uncertain, all contingent on work that continues in laboratories and conference rooms across the world. Fusion remains, as of this moment, an unfinished story. The science is sound. Fusion works. We have seen it in tokamaks and laser chambers, in experiments that release more energy than they consume, in plasmas that burn for minutes or seconds or fractions of seconds. The question is not whether fusion is possible, but whether we can make it practical, economical, safe, and sustained. The obstacles are real. Neutron damage erodes materials. Plasma instabilities disrupt confinement. Tritium must be bred and handled carefully. Heat must be extracted without melting components. Systems must integrate seamlessly. Costs must compete with alternatives. Timelines stretch across decades. Public and political support must endure through setbacks and delays. Yet progress continues. Each experiment adds knowledge. Each new material withstands a little more punishment. Each improvement in magnets or lasers or computational models brings the goal incrementally closer. The community of fusion researchers, thousands strong, patient and stubborn, presses forward. China's investments, Europe's collaboration, America's private ventures, each represents a different path, a different philosophy, a different bet on how fusion might be achieved. No one knows which approach will succeed or whether success will require all of them, each contributing pieces that only together form a complete solution. The diversity of effort is strength, hedging against the failure of any single strategy. Fusion has been called the energy of the future, perpetually so. The joke stings because it contains truth, but it also contains hope. The future does arrive, eventually, and when it does, it often looks different than we imagined. Technologies dismissed as impossible become mundane. Timelines that seemed hopelessly long prove, in hindsight, to have been necessary. We do not know if fusion will power the world in 50 years, or 100, or ever. We do know that the pursuit itself is valuable. It pushes the boundaries of knowledge. It trains generations of scientists and engineers. It fosters international collaboration, however imperfect. It reminds us that some problems are worth solving even if the solution takes lifetimes. The stellar furnace, the dream of infinite power, is both metaphor and reality. Metaphor for human ambition, for the desire to transcend limits, to reach beyond what is given and grasp what is possible. Reality in the sense that the physics is real, the experiments are real, the slow accumulation of understanding is real. If fusion succeeds, it will not save us from every challenge. It will not eliminate inequality, resolve conflicts, or restore ecosystems already lost. It will be one tool among many, part of a broader transformation toward sustainability, toward a relationship with energy that does not exhaust the planet or imperil future generations. It will be imperfect, complex, demanding of maintenance and care, like every human technology. But it might also be extraordinary. It might light cities without burning carbon. It might power industries without poisoning air or water. It might offer a measure of security to nations vulnerable to energy dependence. It might make possible things we have not yet imagined. As you settle into rest, consider the quiet fire. Not the roar of combustion, not the chain reaction of fission, but the controlled merging of atoms, the process that has burned in stars since the universe began. Consider the patience required to bring that process to Earth, the decades of work, the setbacks endured, the knowledge slowly won. Consider the people who have devoted careers to this dream, who will not see its completion, who plant seeds for orchards they will never walk beneath. Consider the engineers troubleshooting plasma instabilities at 3 in the morning, the materials scientists irradiating samples in test reactors, the policymakers negotiating international agreements, the students learning the physics, carrying the work forward. Fusion is not inevitable. It is not guaranteed. It is only possible, and that possibility rests on continued effort, on resources committed, on curiosity sustained. The story is not finished. It unfolds still, in laboratories in China and France and California and Germany and Korea and Japan, in private companies and national labs, in simulations and experiments, in the slow, patient work of turning dreams into reality. The stellar furnace burns, out there, in the sun and in every star. Whether we can kindle that fire here, hold it steady, and draw from it the energy we need, remains to be seen. The attempt is underway. The outcome is uncertain. The journey, however long, is worth taking. Rest now, knowing that while you sleep, someone somewhere is working, measuring plasma temperatures, refining magnet designs, analyzing neutron fluxes, solving one more small problem on the long road to fusion energy. The dream persists. The work continues. The future, whatever it holds, will be shaped by choices made in pursuit of that quiet fire. Let that thought settle gently, a small comfort in the vastness of night. The stars burn on. We reach toward them still,